Okay, this stuff's pretty hard.
What do you mean? It's easy.
Yeah, very easy.
Okay, let me explain. This squiggly x right here is chi-squared.
Okay.
It is equal to this equation over here. Starting with this weird looking e, it's called sigma. That's the sum of all of the times you do this equation over here.
And what does that mean?
Well, this formula is meant to calculate categories and data inputs based on your studies and whatnot, as well as what you estimate would happen.
Okay.
Okay, let me give you an example. Let's say you took a population of 200 people and studied them and asked them what their favorite pet is. Dogs, cats, and other. And then you separate them by gender, male and female. Well, the reason we gather all this data is to determine whether or not the null hypothesis is true. Here it is represented as H0.
Huh?
No, the null hypothesis. It's usually represented as A is not equal to B. In this case, that would mean gender does not correlate with preference for pets.
So we're trying to prove that they do correlate.
Not exactly. We can only have evidence to disprove the hypothesis.
So we can prove it does?
No, that's not really how the science works.
Bet.
This is where the alternate hypothesis comes in, represented as H1, meaning that A does equal B, so that would mean gender does or maybe correlate with pet preference.
So we're proving it does.
We can't exactly prove it does. We can only reject the hypothesis and say that it might be true.
But wait, where does this O and E come from?
It's a good thing you asked. I was just getting there. This is where our data comes in. We have our independent variables, which are our males and females, as well as their answers. That's our observed data. That's what the O stands for.
Oh.
Yes. Now we have to estimate what the answer should be if the null were in fact true. That's where we solve for E.
How do we do that?
You just add the independent variables, take the sum of that independent variables, multiply that by the sum of the dependent variables, and then divide that by the population.
Hey, that's easy.
I told you. So, with that final input, you have the estimated value for that one specific data input. Now you just have to do that for each data set.
So we're not done yet?
Nope. Now we have all of our O's and E's.
Took forever, but okay.
Now we put those numbers into this equation right here, once for each data set.
Oh man.
Okay, now you take the sum of those inputs and ta-da, you have chi-squared.
Woo! We're done.
But wait, there's more.
Yay.
We then put chi-squared on this curve right here, and from then on we determine the critical value.
How do we do that?
Easy. You just take this chi-square chart, available at any bookstore. You then determine the degrees of freedom, which is determined by subtracting 1 out of all your categories. In our case, we have 3 categories, minus 1, that's 2.
But what does that...
Then you locate the alpha, which is usually given to you, and you compare it to where your category lands under. In our case, our alpha is 0.5, so that's 2 at 0.5. Our critical point is 5.991. Alright, that's where this curve comes in. Your critical value is this point, and anything to the right of that is the rejection zone.
What does that mean?
Well, if your chi-square lands in here, then your null is rejected, meaning it's disproven. And in this example, it is disproven.
Neato, what else?
That's it, we rejected the null. That's what it means, a type 1 error.
But what's a type 1 error?
Don't worry about it.